Good evening, and welcome to the Mound Science and Energy Museum Seminar Series, virtual style, via WebEx. Today's presentation is being given on Wednesday, April 28th, 2021, and my name is Bob Bowman, and I am their host tonight. I'm on the board of directors of the Mound Museum Association. And it's my pleasure to introduce our two speakers tonight. Both of them are former Mound employees with a long career in science and research. And tonight they're going to give a most interesting presentation entitled The Art of Adapting Mass Spectroscopy to Efficiently Analyze Your Process and Produce the Data You Need. So without further ado, here are Doug McClelland and Bob Ellefson.
This is Doug McClelland. My co-presenter is Dr. Bob Ellefson. We're with Mound Technical Solutions, located just up the road from the Mound Museum on the site of the former Mound Lab, now the Mound Business Park. And we're here to talk about the art of adapting mass spec to efficiently analyze your process and produce the data you need. The Quadrupole Mass Spec, you may hear that referred to as a QMS, just a simple mass spec MS, or you may hear the term RGA, residual gas analyzer. We're talking about all the same instrument. And in this discussion, we're going to go over applications of the mass spec, and we're actually going to have a demonstration of an application for the unit. We're going to go over practical integration and configuration of the mass spec, as well as demonstrating how that is integrated, and discuss the Mound Technical Solutions hardware and software products that make this a little bit easier for your application. So the Quadrupole Mass Spec is a very versatile tool. It provides us a wide range of measurement. Not only one species of gas, but the total composition of gas is measured. And not just at high concentrations, but we go all the way from 100% down in the parts per million measurement. So the mass spec identifies what the composition of your gas sample is. And so let's talk about how is that data presented? Well, it's presented in what's called a mass to charge ratio. Mass spec looks at each element. If you remember your periodic table, each element had a mass value on it. We'll round that value off to a whole number, and that'll be the AMU, the atomic mass unit that's assigned to that element. So the Quadrupole Mass Spec scans from the lowest mass to the highest mass. Does this incredibly quickly, but each one is measured individually, and the ion current is measured for each mass. And so the stronger that ion current, the higher that signal, the more of that particular element is present in your gas sample. Likewise, the lower that ion current, the less of that particular element is present in your gas sample. So the data looks like the mass spectrum presented in the lower right-hand corner of the screen here, where we have the spectrum for carbon dioxide. And you'll see a very large primary peak at mass 44, which is our carbon dioxide. And you'll also see fragment peaks, and these peaks are looking at the carbon monoxide and the individual carbon and oxygen. So we have a spectrum there that's one snapshot in time of the gas sample containing carbon dioxide. So why would we use the mass spec? Well, like we talked about, to identify the composition of our gas. The nice thing is we're able to have a tool that not only measures a couple decades, but actually gives you a wide dynamic range of measurement, all the way from 100% of a particular element composition down into the parts per million. So we're able to look at proportionality of our composition, as well as small elements that can be contaminants and so on. We're also able to identify things that we may not have expected to see, because after all, we're able to not just look for one or two specific things, but we get a whole spectrum of elements that are in there. So we're accurately able to see these unexpected things, and we're able to use measurements of one element to confirm the total mixture. For instance, if I'm looking at a gas from a cylinder of room air, that typically will not have argon in it. But if I'm sampling my room air, I'll see that 1% argon. So I can kind of use these other measurements to confirm, was that sample from room air or was it from a synthetic cylinder. Now the mass spec does all this incredibly quickly, as I said. In fact, the limiting factor is not the mass spec itself. It's not the measurement. It's introducing the sample into the mass spec for measurement. And so that's the gist of what we're talking about here tonight. But the idea that it does this so quickly, we're able to use one mass spec to measure multiple sample points. So one mass spec can serve as to measure the inlet, the intermediate, and the outlet of a process. It can also serve to have a periodically introduce a calibration standard to verify your measurements so that you know you have a very accurate measurement at all times during your operation. How is it used? At DOE Mound Lab, Dr. Ellefson was the expert, and he was the science fellow here at Mound in charge of the mass spec operations. And if you'd like to see how the mass spec was used in the DOE Mound Lab, I would encourage you to go to the Mound Museum YouTube channel, take a look at the weapons component testing and fusion research presentation that Bob has posted there. And that'll show you some applications spec in the DOE lab. In the private sector, at our company, at Mound Technical Solutions, we use it for a variety of things on a routine basis. We use it for monitoring of fuel cell effluents, which we'll discuss, the evaluation of gas quality. So hydrogen fuel that goes into fuel cells must be very pure. We've used it to identify impurities and quality of electrolysis produced hydrogen. We've used it to identify impurities in other feed gases, such as weld cover gases and so on. Quality performance. So we certify product as it comes off of assembly. We actually use the mass spec to verify that quality. We'll talk about that in more detail. And we also help our customers that come to us to develop specific sensors. We'll have people come to us with novel new ideas of ways to sense things, and they'll want us to help them bring that into beta testing and get it ready to market. And so we'll use the mass spec as we're developing their sensors to concur the information they're getting and to help us with that sampling. Now, in general, Dr. Ellefson, I might note, when he retired from Mound, spent 10 years with INFICON, manufacturer of mass specs, and actually his group was responsible for producing the Transpector QMS, of which you'll see demonstrated here in this presentation. A large market for mass spec is in the semiconductor industry, and they'll use it as a tool to guide them through to manage their deposition processes. And so you'll see a lot of the concentration of application is in this area, and Mound Technical Solutions and our forte is really in helping you to customize this tool for use in your specific application. So let's go into what some of these general applications might be. We're going to break this down into three main categories. The first being quality assurance, the second being ambient environmental analysis, and the third being manufacturing process monitoring. Let's look at that first category, the first application of quality assurance. One of our products is an oxidizer. So this product brings in a sample of typically air with a small amount of hydrogen. We want all that hydrogen to be oxidized completely so that we have no hydrogen on the output and all water vapor on the output. We want to translate that hydrogen coming into water vapor going out. And so every one of our products goes through this evaluation. And this is an illustration of the mass spec evaluating the oxidizer in one of our products. The purpose of this is to verify and to certify the product is doing it better than 99.9% conversion of all hydrogen coming in into water going out. So let's talk about how that looks. Here's a test result. This is the output of the mass spectrometer. And what you'll see here are the various plots. You'll see in sort of a column format, you'll see the variation of inlet to outlet, and so on. And where you see that inlet, just under the word inlet, you'll see a red plot. And that red plot is the hydrogen plot. You'll notice that it's right at 3% measurement. That's the hydrogen coming into the system. Above that red plot, you'll see a blue line, which is the oxygen, and a black line, which is the nitrogen. So that's the air that's in the system going through our sample. Below the red line, you'll see a lighter blue line. That trace is the water vapor. And you'll notice that that's very curved. And you'll notice that it starts out high, and it's at its lowest point just as we leave the inlet. And that's because water vapor is very tenacious. It's going to stay on all the surfaces. And this is where I was talking about the mass spec takes its measurements very quickly. The issue is getting the sample. The new sample coming in must completely replace the old sample, the previous sample, in order to get an accurate measurement of that. Anything remaining from the previous sample will also be measured from the new sample. So we're seeing as we alternate inlet to outlet, the water vapor that you see present on the outlet, notice that that light blue trace is higher on the outlet. Actually, when we go to the inlet, it takes that time for it to come off the surfaces and to give us the lower measurement. But what we're seeing here is highly efficient. We're seeing not only are we converting the 99.9% of the hydrogen, which is that red line across the bottom is the 0.1% of our 3%. Not only do we have all the hydrogen below that, but we don't even have a measurable concentration of hydrogen. So we're not able to detect it with our system. So we've got very good efficiency of oxidation, and that's one application. Second application I want to talk about is the ambient environmental analysis. Now, we introduced the mass spec into our product lines as part of our fuel cell and test instrumentation. And the thing here is that when you're introducing fuel cells, the mass spec can be a valuable tool in developing the fuel cell and analyzing it during its development. Also, when you're done and you have the final product, it's a great tool for analyzing safety. So OSHA's requirements for environmental emissions are very tight, very low. You'll see in that table in the lower right-hand corner that these constituents of concern are in the ppm level. So we're looking at very small effluents. And so we're detecting to see if these products produce effluents that might be of harm or of concern. So the first area example I want to talk about is an evaluation of a reformed methanol fuel cell. Now, in this case, a reformed methanol fuel cell uses methanol as fuel. It has a built-in reformer that converts the methanol over to hydrogen for fuel, and there's a potential that that reformation process may be incomplete. And indeed, when we evaluated this product, we found it on its way to converting that methanol to hydrogen. We were seeing large amounts of carbon monoxide and formaldehyde in our effluents. And so we were able to communicate that to our military customer. They were quite happy to be made aware of it before they exposed people to this concern. Likewise, we were able to work very closely with the manufacturer of the product and help them with our data to understand what was going on with their product and to improve their product to the point where today they have a product not producing these harmful emissions. Another example in the fuel cell arena is a very large 1.5 kilowatt generator. Now this is a direct methanol where it uses methanol directly to produce the fuel, and it is therefore not as likely to produce effluents of concern. But again, the customer is using, military customer is one of the first customers. They want to be sure that these very new products are safe and effective. So we do what is called an environmental stress screening of the product. So not only are we evaluating the product, but we're operating it in real world conditions and environments that you would expect. So we've got the unit under load, the fuel cell's producing power, that power is being drained, it's producing more. We're operating it in an oven. You'll see that the unit's placed inside an oven here, and it's operated from 104 degrees F down to 20 degrees F to simulate the changing conditions that it will experience in real life. And we're monitoring the effluents with the mass spec as shown here in the photograph. We're happy to report that this unit performed excellent as far as operation and absolutely no effluents to speak of whatsoever. Third application that we talked about is manufacturing process monitoring. This is probably maybe the largest category. This is where we talk about things such as, some of them are proprietary, where we'll have customers come and they'll want us to help them with their secret sauce, so to speak. And then this is where we help them to sample, do things. But in general, we're talking about things such as leak checking. You might be a manufacturer that puts your product in a container and you want to verify that it's leak tight before getting rid of it. So you may be a manufacturer of small CO2 cartridges. And as those are coming off the assembly line before you ship them to the stores, you want to make sure they're leak tight. Mass spec can serve in that application. Similar things to that for leak checking. That's very popular. Again, the deposition process control, that's something that we see very often as an application for the mass spec. Verification of feed gas is used. So we want to verify that the feed gas into the process is of the right purity and so on. And then finally, we're going to look into an example of where we have inert atmosphere manufacturing cells. In the DOE world, we call these glove boxes. Glove box is a common term. This is an environment where you want to keep the oxygen out. You'll have a nitrogen or argon glove box. And typically, these boxes are monitored with electrochemical cells to detect oxygen levels specifically. And so we're going to take a look here at a video of an engineering study that we've done, sort of an example of how we would look at using the mass spec to monitor not just one, but multiple glove boxes. So we're sharing one resource of the mass spec to monitor multiple glove boxes. We want to know, can we sample these multiple glove boxes and get the measurement quickly and efficiently? Can we get a quality measurement, an accurate measurement, a very sensitive measurement, and still do all this with one mass spec? So I'm going to start this video, and after the video, we will go on and some more discussion.
Hello, welcome to Mound Technical Solutions. We're here in our lab today to demonstrate the quadrupole mass spec used to monitor inert atmosphere manufacturing cells, otherwise known as glove boxes. So what we have is our INFICON closed ion source quadrupole mass spec sensor inside of our sample chamber. The sample chamber is a T configuration mounted atop of our vacuum station. Our two-stage vacuum station is a turbomolecular pump backed up by a diaphragm roughing pump. The inlet system, in this case, is one of our multiplexed inputs. This particular one is an 8 capillary input switched by electronic valves, so we can automatically or manually select which of the 8 capillaries we want to introduce to the sample chamber. In order to conduct this test, which is basically a feasibility study where we use existing hardware and evaluate the ability of the mass spec to perform the function, i.e. measure the oxygen content in multiple glove boxes. Can we do that quick enough? Can we do it in a rapid succession by multiplexing the 1 unit amongst the 8 or more glove boxes? And can we get the accurate data that we want? And what does that data look like? So we've had our gas manufacturer supply us with 2%, 4%, and 6% oxygen and nitrogen gas cylinder standards. So these cylinders then supply 3 capillaries to our input, 2%, 4%, and 6% gases. And we have a 4th capillary out here in the room air, which will bring in our 21% oxygen from room air into the mass spec. So this is the test configuration. Now let's move in and take a look at the test itself. Okay, here we have the test started. This is the typical data that you'll see from your mass spec. This is the mass spectrum here at the bottom. The lowest mass to the left, the higher masses to the right, and the intensity of each reflected on this plot. The same data is expressed in digital format over here with the mass unit in this column and the intensity of ion current in that column. And then we plot the real-time data over here. So over time, every 3 seconds we acquire a new sample. We're acquiring 10 samples on each capillary. So each capillary will be monitored for 30 seconds. That's 3 seconds per data point, 10 samples per capillary. So that's our 30-second cycle time. And you'll see that data come across from the mass spec. Right now, we're sampling the room air capillary, it tells me here. That's capillary number 3, room air. So we're out here in the air, and we see that the highest plot at that point is the black trace. The black trace is associated with mass 28. Mass 28 is our nitrogen component. The second highest plot is this blue trace. The blue trace is associated with mass 32, which is our oxygen component. And then below that, we'll have some other components which will vary depending upon whether or not they'll be there, whether or not we're sampling room air or the cylinder gases, as we'll talk about in a moment. So this is all very good data, but we can present it in a much more intuitive way. So Mound Technical Solutions has a software package we call our Mass Spec Interpreter. So if we switch over here to our chemistry screen, we're able to express that same data presented as a mole percentage. So now we have the mole percent of each gas. It's presented in a real-time plot. These plot points are expressed as mole percent on our 5-decade logarithmic scale. And you'll see that the same data expressed in digital format as we cycle through and fill in the appropriate data. So right now we've transitioned from our 2% to our 4% gas standard. So you'll see that when we went from our 2% standard, we actually measured 2.025% oxygen in that standard. So we got a very good answer. You'll notice that we have no argon really to speak of, 30 parts per million argon, and very low water vapor in that, maybe 0.1% water vapor. And you'll see that when we got to our 4% and our 6%, the water vapor went even lower. But you'll notice as we measured our three standards, the 2%, the 4%, and the 6%, we get very accurate results of these measurements, very accurate answers. And you'll notice the speed at which we transition from 2 to 4%. You'll see these plots, it took virtually, we had the right answer on the first data point, but certainly within 2 or 3 data points, which is 4 to 6 seconds, we had the appropriate answer as we transition from 2% to 4%. The same goes for 4% to 6%. What's happening is during this transition, we're leaving the old gas, evacuating it, introducing new gas, and there's a finite amount of time where these gases co-mix. And so you'll see remnants of the old gas showing up in the first samples on the new capillary. So that's not so pronounced now, but we'll see it here in a moment. We've gone through our background measurement where we have no data to present as a mole percent. And we're now sampling from our room air capillary. The room air capillary out here in the air, so it's measuring the same air I'm breathing, is of course measuring the strongest signal coming from the nitrogen, which is 77.7%. The oxygen component is 20.5%, and the balance of that is made up by our argon at 1%, and our water vapor at just over 0.7%. So you'll see we've got quite a bit going on with our room air gas that doesn't happen within our cylinder gases. So you'll see that water vapor, the water concentration in our cylinder gases is much, much lower than the water vapor coming from the room air. The room air is 0.7%. The cylinders, the second two cylinders, show that they dry out much better. I suspect if we sampled this capillary a little longer, it would even show that that gas is indeed drier. But we get a very good answer within our allotted 30 seconds, and we also pick up some data that we weren't necessarily looking for. We observed that the argon component that was present in the room air sample is not present in the cylinder gases. We have trace amount that carried over that we didn't get evacuated from our 2%, but by the time we got to our 4% and 6% cylinders, we've successfully removed all of the traces of the argon. What we do see is this yellow plot, which is our carbon dioxide. The carbon dioxide in the room air capillary out here is 500 parts per million, which is to be expected. But you'll notice that we really have 20 parts per million, which is very low carbon dioxide coming from the manufacturer's synthetic cylinder gases. So we're able to measure some other things going on in our processing cells other than just oxygen. But we've seen that we're able to transition, certainly within our 30 seconds, to get the appropriate answers of 2%, 4%, and 6%. And here's our 21% minus the balance that was taken by the water vapor. And so we're getting very good measurements very quickly in less than 30 seconds per capillary. So we can look at how many boxes do we want to sample, say times 30 seconds each, and that'll give us a time for our sample cycle time. We can observe the accuracy of the data, and now the one thing left to do is to observe how reproducible this is. So that's going to require us to leave it run for a little while, and we'll see if this data replicates itself time after time. Do we get the same accurate answers, or do we notice a drift over time? And so in all reality, for this test to go on, we would run it for many hours to see what kind of results we would have. But for this demonstration, we'll just leave it go for just a little while. Okay, so what we've done here is let it run for a few more cycles. And what we see is that, yes, indeed, we do have reproducibility of data. We have consistency with our measurement of oxygen at 21%, at our 2%, and our 4 and 6%. So we're interested to see that the argon that's present with our room air goes away in our cylinder gas each time. Same thing goes for the carbon dioxide and the water vapor trace. So we've basically got a good foundation for using the mass spec in this application, and we'll just continue to evaluate and test. If we can help you with your applications or help you design some hardware, we'd be glad to help. So if you need anything.
I hope that was informative. The rest of our discussion now talks about the integration, how to customize the mass spec to do exactly what you need. The mass spec has several components, and so let's talk about what these components are. They include the sensor, the sample chamber, the vacuum system, the sample inlet, and the data acquisition and control unit. So these components are all needed to make a mass spec work. And so let's see how these components come together. The sensor, now Bob's going to go into this in more detail later, but let me just tell you for now that the sensor can be divided into two main categories. It comes in two varieties, an open ion source, OIS, and a closed ion source, CIS. Now the open ion source enjoys a lower cost and a little bit easier maintenance. However, the closed ion source gives you a little bit wider dynamic range of operation, measurement, and a wider operating pressure range, as well as a better signal to noise ratio, so you get better sensitivity. Now here's a picture of the sensor. The sensor in the unit that you saw in the video was the closed ion source INFICON sensor. So this is our quadrupole sensor in the upper photograph. The sensor by itself. In the photograph below it, you see the sensor integrated with its electronics package. So this is the Quadrupole Mass Spec product as you would purchase it. Now we take that sensor and we have to operate it in a vacuum envelope. So that's our sample chamber. Our sample chamber is shown here in the photograph as a T configuration with complex flanges interfacing the inlet, the outlet, and the connection to the vacuum station. And we're fortunate that our INFICON unit is able to provide us with the total pressure of the sample as part of its measurement. But if your mass spec is not providing you with the sample pressure measurement, you'll need a fourth port on your sample chamber in order to install a pressure transducer to give you that pressure measurement in your sample chamber. The vacuum system, of course, is very important. The mass spec operates in the range of 10 to the minus 4 to 10 to the minus 6 torr. We want this vacuum system to be a dry system, no oil, because we want to prevent the potential of having backstreaming of the oil and contaminants back into our sample measurement. Now, what you saw demonstrated and what's very common is a roughing diaphragm pump supporting a turbomolecular pump into one integrated system. And we're actually making dual use of our vacuum system. So not only is the vacuum station serving to provide the vacuum for the mass spec itself, but we're also using it for a second purpose of bringing the sample, moving the sample from the source through the capillaries into our sample inlet and into the sample chamber. So we have two uses for the one system. Now the sample inlet, this is where we really find the most efficiency in getting your sample integrated in quickly, sampled quickly, efficiently, and accurately. The sample inlet translates the sample from the source into the mass spec sample chamber. So it can be a single inlet or a multiplexed inlet, bringing in multiple capillaries into one. In any case, they'll do this translation through what we call a precision leak. This is a uniquely configured orifice that matches your sample with the vacuum inside your sample chamber. And the idea of this sample inlet system is to minimize the volume, minimize surface area, minimize dead spaces. You want the components to be high durability. You want your valves to last through many, many cycles and have great performance and great leak-tight integrity. And it's this inlet system where you protect yourself and give yourself the best quality of measurement. Any leaks will interfere significantly with your measurements. So you want to have a very leak-tight inlet system, and you want to have a very quick introduction of the new sample and replacement of the old sample with the new sample. And so this is something that we do, and if you have any questions, we'd be glad to work with you on a custom design. But this is the part of your system where you're going to make a significant difference between having an okay operation with your mass spec and having a very efficient, highly effective use of the mass spec to monitor your process. Lastly, I want to talk about the data acquisition and control system. This is the software that manages the mass spec itself, tells the mass spec what its configuration is, and receives the data from the mass spec. It also has to simultaneously control that sample inlet and manage it. And the thing is, this needs to be a fully integrated system so that we know when we're sampling, from where we're sampling, and then marry the data with that. So it needs to be a seamless system, fully integrated. We also want to present that data in a friendly manner so that you can observe in real time what's going on. And potentially with your application, you may need to trigger alarms, alter a process, or do something else. So we'll have some specific software interfaces to go directly into your process control. And finally, we have data storage so that we can go back and look at the data for future reference. So overall, as you saw in the video, here's the total system integration. You have the data acquisition and control system, which is our software on the computer. You have the sensor, and you have the sensor located inside the sample chamber. You have a sample inlet, which can be single or multiplexed, and you have a vacuum station. We're going to take a look at a video now that goes into this systems integration and walks you through how the system goes together and what this looks like as far as data coming out. So we'll go on and take a look at this video.
Hello, welcome to Mound Technical Solutions. We're here in the lab today to discuss the Quadrupole Mass Spectrometer. We're going to go over just the general configuration of the instrument and how to use it in an application. So let's dig right in and talk about the various components of the mass spec. What we have is an INFICON quadrupole closed ion source mass spectrometer, RGA. The electronics package here, the sensor located within our sample chamber. Our T-shaped sample chamber has a complex flange interface to the electronics module sensor, to the sample inlet, and to our vacuum station. Our vacuum station is a two-stage turbomolecular pump backed up by a diaphragm roughing pump. The system serves not only to evacuate the sample chamber to service the mass spec for operation, but also serves to pull the sample through our capillaries and draw that sample into the inlet. Our sample inlet module is a multiplex 8 inlet, 8 capillaries into one inlet, And these are electronic valves, not pneumatic, so we're not reliant on house air, but are self-contained, all electronic, highly durable, and highly reliable electronic valves. So these 8 inlet capillaries are actually these 16th inch OD capillaries. These are stainless steel. What may vary with a capillary are the inner diameter. The bore throughout the center of the capillary may be various sizes based upon the operating pressure and the length of the capillary in your specific application. The capillaries can come in different materials and may have different coatings. Dr. Ellefson has an excellent presentation discussing his analysis of various capillaries in various applications, and I would urge you, if that's of interest to you, to get a hold of us, and we'll get that information to you. So we have 8 capillaries capable of bringing in samples, and we're able to select which of those capillaries we're sampling at a specific time into our sample chamber. So that's our mass spec system, fully integrated here. If you need any help integrating your mass spec with sample chambers, with the interface between the mass spec and the sample chamber, the design of the sample chamber itself, the integration to a vacuum station, or specifically the inlet system. We have various configurations of inlet modules to facilitate various custom applications. So now let's move in and talk about the computer control and the software involved. Okay, so here we are with our setup screen for our mass spec control. This screen configures the mass spectrometer itself. It configures the inlet system, which capillaries are sampling. We can provide nicknames for them to make it easier for us to track, and allows us to set up automatic modes of sampling so that we can configure which capillaries are active, how long to sample on each capillary, and configure things also such as the background measurement, how that is performed, as well as specific mass spectrometer configurations such as whether or not the electron multiplier is activated or what voltage that may be set at. So let's go a step deeper into this configuration and let's look at our calibration screen. Here's the calibration. Now the calibration of a mass spec is performed by introducing a gas standard into the inlet. So we have our gas supplier provide a known concentration of gas to us, and we introduce that into the mass spec and we look at the response, and we can adjust the sensitivity of the mass spec accordingly. We've found our unit to be particularly stable over the past decade of operation and very little need to adjust the sensitivities. This also has our interpreter matrix, which allows us to configure various gas species that we're interested in analyzing. We can add or subtract from these species, and we can configure specifically what we're interested in looking at and how that is presented onto the screen. So with that all configured, let's back out of this and take a look at our test itself. We'll open up our live analyzer, and we've got our vacuum station up and running, so the inlet system is already pumped down. Let's go ahead and while that's happening, let's go ahead and pump down our inlet itself. We've got our sample chamber evacuated. Now we're pumping down our inlet, and shortly when it sees sufficient vacuum for our inlet, it'll give us the green light. We're good to go. Now we can, let's set up a test that is run in a manual mode. Let's do our background in a continuous update, meaning that we'll continuously update that background. And let's sample capillary number 3, which is out here in the room air. So we've got this capillary here just out monitoring the ambient air in the room. So this is going to be a manually controlled test. We'll start the test, and we'll call this test Demo 1. And we'll start the test. And at this point, the mass spec is getting its instructions from the computer as far as the configuration. The inlet module is being configured by the computer to tell it which capillary to sample, number 3 in this case. And we're bringing in the data from the mass spec, which is that mass to charge data, which is the mass unit compared to the ion current detected from each. So we can actually go and open up a digital window here for you, and this should make it a little bit easier for us to see what's going on here. There we go. And get that window down here out of the way for us so that we can see the data coming in. So what you find is that you've got various mass units assigned various colors that are being plotted, and associated with that are the ion and current intensities over here. So the highest ion current, the highest intensity, is the most significant component in the gas. So you'll find out with this that the highest level of current is this black plot. The black plot associates with mass 28. Mass 28, as we know, is our nitrogen component. And so in our room atmosphere, nitrogen is naturally the most prolific component. The second is this royal blue line. The royal blue line is associated with mass 32, and as we know, mass 32 is associated with oxygen, so that is our oxygen component. And below that, we're going to find things such as the gray plot, and which is argon, mass 40, and we'll see the water plot, which is the lighter blue, mass 18 plot. Now the water plot will vary as the system samples. That it tends to start out pulling any moisture that's already in the capillary and in the sample chamber, getting that out of the system, so we'll see that dry over time. As you can see, this is very good information, but it's not quite as user-friendly as we would like, so we've built an interpreter into this. We put this on our chemistry screen. And so with this, we're actually able to observe that same data presented in mole percentage information. So now that information that you had before, which was giving you mass units, is now converted into which component of gas that represents. So for instance, our nitrogen component is still the black line. We see it at just under 78%. We see our oxygen component, which is the royal blue, which is just under 21%. And then we see our argon, which is the gray line, and we see that that is just at 1% in air. And below that, we'll see some water vapor. The water vapor is the lighter blue, and that's at between 3 and 0.4% water vapor. Below that, we have things in the air such as carbon dioxide, carbon monoxide, some stray things that may have been left over from other samples still coming off the wall. But this gas looks very clean in all reality. In fact, the number that you're seeing here is a percentage. So while we have 78 and 21%, on some components, such as nitrogen and oxygen, you'll see some very small numbers, such as the carbon dioxide, this yellow plot. On our logarithmic scale, we're showing this logarithmically so that we can present all 5 decades. We've got 5 decades of information reporting here. And so we can see that the carbon dioxide level in here is down at the 540 parts per million. So this last digit after the decimal place, the third digit out, is 10 parts per million. So that's just how sensitive we're looking. We're going from 10 parts per million up to full percentages of gases. And so now to take this a step further, let's go take a look behind all this data. This is the CSV file that's actually produced by the data. This is what the system saves to allow you to call the information up later to look at it again. But I wanted to give you an idea for just the extent, the amount of data, the quantity of data that's being saved and acquired. What we have is a time and date stamp with each data point. Each of these rows represents one data stream, and each of these rows is going to be 3 seconds apart. So each data stream is an additional 3 seconds. So we not only have a time stamp, but we have a capillary stamp as well, so that we know where's the sample coming from. So now we know when it was taken and from where it was taken. And then all these rows here are the mass spec data providing us with that full spectrum of information for each sample. So every 3 seconds we're appending this, so you can see that data becomes quite large over time. And so you've got quite a lot of information to look at and to keep track of, but with the properly configured hardware and software, you're able to get a very comprehensive data set from your mass spec and present it in a very comprehensive and understanding way. So I hope you've appreciated this. Thank you for your time. Goodbye.
Hello, I'm Bob Ellefson, and I want to talk to you about some of the details of the gas dynamics of the sampling system and the analyzer, the Quadrupole Mass Spec. If you look in the lower left-hand side, we represent a process here where the gas typically is a half a atmosphere to 3 atmospheres, and we sample from that by inserting a capillary as a T into the flowing process. The gas goes through the capillary up to a manifold, which is at about a pressure of like 2 to 10 torr, and then the gas is drawn into this interstage pump of the turbomolecular pump. The net result is a flow of the gas with a transit time of about 0.4 of a second through all of the sampling plumbing. And this makes a speed of the gas flow something like 3.8 meters per second. So that's the way we can get a rapid update of the composition in the actual process. The actual flow through the capillary is dependent on a constant, the internal diameter of the capillary to the 4th power, the pressure squared, and inversely with the viscosity and the length of the capillary. So the variables we have are the ID of the capillary and the length of it. And these are designed to, first of all, connect to the process and bring it to the mass spectrometer at some central location. But the other part of it is to make sure that we get the flow design such that you don't overload the pump. So the gas comes up to the 10 torr position, and at that point we have a molecular leak, which is a laser drilled hole through a gasket, and that allows the gas, or a small fraction of it, to flow directly into the closed ion source. So the preferred ionizer for this operation is a closed ion source, and we'll see why in just a second. What we've shown here in red is the gas sample we're tracing, and the light red or pinkish indication in the closed ion source is that the pressure is reduced from an atmosphere down to 3 × 10⁻⁴ torr, which is about 1 part per million of the total atmosphere. But that's the pressure we need in the ion source in order for the ionization process to work. There's electrons that come in from the side here underneath the closed ion source, forms ions which are extracted by various voltages and injected into the quadrupole mass filter. Mass filter is operated with RF and DC potentials that are scanned to look at the mass spectrum of the whole range that we're interested in. And we then record the ion currents that come out in an electrometer within the quadrupole electronics. So all of this is a package that the goal for the user is to provide a representative sample. The gas dynamics of this is that the capillary transports the gas as a viscous flow so that the composition is retained, and then from that viscous flow we have molecular flow through the leak into the mass spectrometer and molecular flow pumping out. The result of that is that the composition is maintained. This could also be done with the open ion source. The major difference is same sampling system design, but from the molecular leak, it produces a pressure of 2 × 10⁻⁵. It's a lower pressure, but it fills the whole vacuum sampling system shown by this little redder system. The idea is then that the ions that are formed in this open ion source, they all have to go through the gas mixture at 10⁻⁵ torr. And as a result, it can have some scattering and some losses. The gas can also react with a larger surface area, and that can have some effects on the result. Here is a test that we assembled to show what would the results be with the open ion source. This has the cross to introduce a separate ion gauge because this one does not produce the total pressure. But this is an open ion source hidden in the side of the stainless steel vacuum system. The gas comes in from the left with capillaries from gas reservoirs or the room air. And to the right here, we show fairly high purity argon and purity nitrogen and air. And the main difference that you can see is in this raw ion current, with air, there's some new species that creep in to give oxygen level and argon and water vapor. We take that raw data and we process it by hand. In this case, we don't have a friendly computer like we have in our CIS system. Basically, we take the raw ion current, subtract the background from it to get the net composition of the gas that was introduced, divided by the sensitivity to get partial pressures. And then we take those partial pressures, sum them up and divide them into the individual partial pressures to give times 100 to give mole% of composition. So we've taken this raw ion current and massaged the data to produce a spectrum like we've seen before, from Doug's system. And here you can see argon is mainly high purity argon, and then the blue color is for the nitrogen high purity. And then with air, the nitrogen goes from being 100% down to 78% with 20.9% oxygen in it, about 1% of argon. And then here the yellow is water vapor that creeps in as we introduce wet air compared to the lower water vapor in the previous N2 that is there. So the answer is you can certainly do compositional analysis with an open ion source and a similar sampling system. But if you look at some of the data, like the oxygen is climbing in intensity as it gets exposed to this oxygen, the surface potentials change slightly, and that affects the sensitivity and ion transmission. And similarly for the argon, we show it going down here. So clearly things are changing due to the surface interactions of the gas with the stainless steel surfaces. To do a direct comparison, on the left is the OIS. It's the same plot as the previous data. And then you look at the CIS data that Doug had shown you earlier, and you see that the air is flat, the oxygen level and the signals are flat. You change to different oxygen standards, and you can see the level rapidly achieves a stable, trustworthy value, as opposed to the drift that is still occurring with the change of gas composition in the OIS. So given for a larger incremental cost, you can go to the CIS, but it's worth the investment for the quality of the data that you have. So what is this data and how do you interpret it? Well, we described that we have a software interpreter because we consider something like 23 standard peaks that are often existing in an atmosphere. You can add additional peaks if you have a special process or something. But amongst all of those, when you ionize them, you not only get the parent molecular ion, you can also get fragment ions. And these fragments can appear at other places. So let's look at the mass spectrums of a few common species here. Nitrogen, the dominant species, is the parent molecular ion at mass 28. There's also a mass 14 peak that appears. In carbon monoxide, that also appears at mass 28. So it also contributes at mass 16 as O+, and mass 12, C+. And so those fragments can occur. And you also can have carbon dioxide giving a 10% fragment at mass 28. So if there's a lot of carbon dioxide present, one would need to correct its composition contribution to the mass 28 peak. Other species that might be present, like formaldehyde, can contribute at mass 28. So all of these need to be corrected. And in our matrix of mathematical corrections to the ion currents, this is all done in real time as we gather the data. Here we show another one, which is oxygen 32, giving a peak at mass 16, which can interfere if you have mass 16 methane. So in our case, what we measure for methane is to look at the mass 15 peak, for which there's a little interference. And so we use mass 15 for methane and mass 17 for ammonia, which also has a 16 peak. So 16 is not a particularly diagnostic peak for us. So all of this data is gathered together and taken rapidly and in real time. The data has a timestamp so that you can sort out how to plot it and where it arrived in time. It identifies what capillary did it come from and labeled this was an air sample. And so you can see all of the different species that we have looked for, and there's some more of them off to the right. That data then is massaged with our data interpreter, and the results of that are shown in this table. We have capillaries. 3 is a air with 3% hydrogen in it. If you look over to the right, there is the black nitrogen, blue oxygen, red 3% of hydrogen, and then argon and other things you might expect to be in air. And then it's the small 2%, 4%, 6% oxygen in nitrogen standards. And those then are shown here. If you look at the actual data, the number for the air is 20.98. And this is using sensitivities that we've used for many, many years. So this is an extremely stable system, which gives confidence in the data result. So if you're going to buy a mass spectrometer and install it to monitor your process, what do you need to consider? Well, we have here a decision matrix that covers by column different things that you need to consider. For example, in the quadrupole sensor, which one should I get? The OIS and save a little cost, or a CIS and get better data? Do you want an FC detector, which is just measuring the raw ion current? Or do you need an electron multiplier to look for low-level values? And then there are other issues on materials and mass range, and that the design of the sample chamber, the design of the vacuum system, and what components do you use? What should the sample inlet design be? How much does it need to present the sample, and what are the control mechanisms you need? And then the data acquisition and control. So a number of things, and of course we would be very happy to help you with your decisions. So a data acquisition and control system controls the mass spec's functions, gathers the data, stores the data. It has a sample inlet that it controls and correlates the data with the data set so that you know what's going on in a particular location or environment. Total pressure of the sample should be known for each measurement as part of our closure to make sure we got accounted for everything. Data analysis converts the ion currents from the master charge species to partial pressures to mole percents, and then plot and give a digital display of those net results as a function of time. The data storage allows you to go back and look at things and do postmortems if you're a customer or you as the customer want to go back and see how it behaved the last time you analyzed it. So in summary, a quadrupole is a very versatile analytical tool. It provides comprehensive data from numerous species that you can select. The measurement range is wide, from like 10 parts per million assured, and you can look a little lower than that, up to 100%. Properly configured, the data comes out rapidly, and it moves from one sampling point to another efficiently. The system can sample multiple processes and share the use of the quadrupole to give you maximum flexibility and usability of your investment. So thank you for watching, and if you have questions, these are our email addresses. You can certainly address the questions to either of us. We'd be most happy to answer your questions, and have a good evening.
Well, thank you, Doug and Bob, for the most enlightening discussion on the role of mass spectroscopy to analyze systems and chemical processes. If you have any questions or want to know more about these technique and information, you'll notice that Bob, Doug left their contact information on one of their last slides, so it's there. You can see it by checking on YouTube. And with that, we'll close the presentation, but except for announcing that our next seminar will be on May the 26th. I will be talking on the story of Monsanto Chemical Company in St. Louis, Dayton, Ohio, and Miamisburg. It's kind of a brief overview of what Monsanto's role was for those of us that were involved. And with that, good night.